Hello, I am Vahid Lotfi, Emeritus Professor of Management Science. In this video, I will demonstrate how to solve a linear programming problem with a minimizing objective function using the graphical solution procedure. Our sample problem consists of having two decision variables and two constraints. So let's get started. Okay. The problem we want to solve is to minimize z equal to 3x1 plus 5x2 subject to 2x1 plus 4x2 greater than or equal to 80 and 3x1 plus 2x2 greater than or equal to 60, and of course our non-negativity constraints x1 and x2 greater than or equal to 0. The first step of the graphical solution procedure is to draw the feasible region. And in order to draw the feasible region, we will take one constraint at a time, make it an equality, plot the line, and identify which side of the line constitutes the feasible region. So if I start with R1, I'll make that an equality, which would be 2x1 plus 4x2 equal to 80. Now I want to identify 2 points, arbitrary points, and connect them so that could form the line associated with this equation. The most convenient points are x1 equal to 0, which would result in x2 equal to 20, and x2 equal to 0, which would result in x1 equal to 40. I will connect those 2 points together. First identify them. There is x1 equal to 0, x2 equal to 20, which is right here, and x2 equal to 0 and x1 equal to 40, which is here. I want to connect those 2 points. So I move my ruler here, like so, and then draw the line. So that line represents this equation. In other words, all pairs of x1 and x2 on that line satisfy that equation. But our constraint is greater than or equal to. So we have to identify which side of this line, the upper part or the lower part, satisfy the inequality. The easiest point to test would be the origin, 0 and 0. If I substitute 0 for x1 and 0 for x2, that is obviously not greater than 80. Therefore, the lower part is infeasible and the upper part constitutes the feasible point, or the feasible region rather. So we draw a little arrow like that, and I'm going to label this constraint as or line as R1. I will continue with a similar process to draw the line associated with the second objective. First, we make it an equality. That would be 3x1 plus 2x2 equal to 60. Then select 2 arbitrary points. Again, for convenience, I let x1 equal to 0, which would give me 2x2 equal to 60, or x2 equal to 30. And then I let x2 equal to 0, which would give me 3x1 equal to 60, or x1 equal to 20. And now I will draw this line. First, identify the 2 points. x1 equal to 0 is here, x2 equal to 30 is here. The second one is x2 equal to 0 and x1 equal to 20, which is here. And so I'll go ahead and draw that line. There is 30 and 20. Once again, we have to identify which side of the line constitutes the feasible region. Again, if we take 0 and 0 and substitute it into this inequality, we notice that the origin does not satisfy the inequality, therefore the lower part is infeasible and the upper part is the feasible part. So we'll make a little arrow like so to signify that is the feasible portion, and I'm going to label this line as R2. Okay, therefore now we know that the region that is comprised of this area here, this unbounded area here, constitutes the feasible region. So I want to now draw the line associated with the objective function. In order to do that, we have to select an arbitrary value for z and then substitute it into the equation of the objective function, and then identify 2 points and connect the 2 points. So I'm going to let z equal to, let's say, 150. In this case, I get 3x1 plus 5x2 equal to 150. Again, the number 150 is arbitrary. And then I let the same thing, x1 equal to 0, which would give me x2 equal to 30. And if I let x2 equal to 0, that would give me x1 equal to 50. We are going to identify these 2 points, x1 equal to 0, x2 equal to 30, and x2 equal to 0, x1 equal to 50, and connect the 2 points together again, as before. A line of objective would be something like that. I'm going to make that a red line to signify that is my objective function. Notice in this case, I want to minimize the objective line. Notice that if I select any point on this line, I get a z value, and that point will be feasible. For example, if I take this point, which is x1 equal to 0 and x2 equal to 30, that satisfies both of these constraints, and that would give me a z value of 150. What we want to do though is to make this as small as possible. Therefore, we are going to lower that point. Notice I'm not changing the inclination all the way until we leave the feasible region. So that point is going to be, this point right here is going to be my optimal solution. And in order to find this point, I have to intersect these two constraints. In order to intersect those two constraints, I will make them equality again. So in this case, it would be 2x1 plus 4x2 equal to 80, and 3x1 plus 2x2 equal to 60. And I want to solve these two simultaneously. One way to do that would be if I take my second equation and multiply the second equation with a -2 and add it to the top equation. Notice I'm eliminating the x2 variable. So let's do that. In this case, I end up with minus 6x1 minus 4x2 equal to minus 120. Now I will add this to the above equation, so I end up with 2x1 minus 6x1 minus 4x2 plus 4x2 equal to 80 minus 120. That gives me minus 4x1 plus 0 equal to minus 40, or x1 equal to 10. I can then substitute this into any one of the two equations in order to find the value of x2. So I'll put it in the first one, which says 2 times 10 plus 4x2 equal to 80, and that gives me 4x2 equal to 80 minus 20, which is 60, or x2 equal to 15. So the optimum point is x1 equal to 10 and x2 equal to 15, and the z value is going to be 3 times 10 plus 5 times 15, which is equal to 30 plus 75, or 105. And that is my optimal solution for this minimization problem. If you liked my video, please subscribe to my channel and click on the like button. Thank you.